So we're going to go over another class of biomolecules, lipids. We're going to cover, basically what they are, which really are a mixed bag. We're going to talk about triglycerides. So my wording says triacylglycerols because that's the more correct term, but I learned it as triglycerides, and most people know it as triglycerides. So that when I can't help myself, I'm going to say triglycerides. So when you see triacylglycerols and you hear me say triglycerides, they're the same thing. Phospholipids, waxes, and I just like saying this word, sphingolipids. It's just fun to say. Before taking this class, I never heard of it, so we're going to talk about it. Things get freaky. When we talk about sphingolipids, these molecules that nature builds are just crazy, crazy stuff. So we're going to just look at those. Steroids are very different than these other molecules, but they still fall in the class of lipids. Then we're going to apply our knowledge of lipids to membranes and talk about the very nature of membranes. What are membranes? And what do they look like? And how do we use them? We're going to talk about lipoproteins and how we can look at the environment. And then we're going to talk about vitamins. So cool. Talk about a little bit of nutrition and what they're used for. And then another class of molecules. I'm not sure if your textbook talks about this too much, but prostaglandins and leukotrienes. I like to cover them briefly because they're a hot area of research. Okay, so what are lipids? The definition is a natural material that are soluble in nonpolar solvent. So it's some sort of biological material that is not soluble in water, soluble in nonpolar solvents. Those solvents can be ether, chloroform, benzene. We don't really have these in our body, thank goodness. We should not. But they're really important. We have lipids in our body. We don't have these solvents in our body. That's what I'm trying to say. They're very important physiologically. It provides a lot of energy. And most importantly, from my standpoint, is they make up membranes. It is really a mixed bag. The only real similarity that they have is that they're natural materials that are soluble in nonpolar solvents. That's really the only thing that they all share. So because they're soluble in nonpolar solvents, they have nonpolar groups. So you can classify lipids at either being open chain with polar heads and nonpolar tails, where the nonpolar tail takes over, or steroids, which are fused rings. So here's our steroids, and these are the other classes that we're going to talk about. So we're going to talk about waxes, which are kind of not very exciting. Triglycerides, we're going to spend a lot of time on triglycerides. Triglycerides can be broken up into fats and oils based on whether they're saturated or unsaturated. Phospholipids are critical in our membranes, and sphingolipids play an important role in signaling. We'll see that in a lot of signaling processes. And then steroids, we'll spend some time talking about those, the legal kind. So fatty acids condensed with glycerol. When I say the word condensed, it means we're putting them together. All right, we're putting fatty acid with glycerol. So a fatty acid, let's start with a fatty acid. What does that mean? A fatty acid, fatty means the nonpolar tail. That's what I mean by the word fatty. And then you have an organic acid. So that's what a fatty acid is. Because it has the nonpolar part and the polar part, we call it amphipathic. I have a bias towards even numbers. When I read a burette, I'm always rounding, estimating to even numbers. I don't know, it's just something that I do. Nature has an even number bias as well. So the length of the carbon chain is always, or not always, but mostly even. And it's pretty long, 12 to 20 carbons. And we don't really see any branches in our fatty acids. Remember our definition of saturated means we're saturated with hydrogens. We don't have any double bonds in a saturated fatty acid. If we see a double bond, then it's going to be an unsaturated fatty acid. We can have more than one. Let's take a look at them. Remember, this chain length, when we have a chain of hydrocarbons, the last slide showed them as a perfect flat straight chain. Really, it's a zigzag. So when we say a straight chain, it's not really straight, it's a zigzag. So here we have a saturated fatty acid, and here we have unsaturated fatty acids. So can we say, what kind of double bond is this, cis or trans? You kind of have to put your head to the side. Trans. And this one is cis. So can you see the similarity between the saturated fatty acid and the trans fatty acid? The shape is the same. And what happens when we have the cis? We have a little kink. Now, when we name our fatty acids, which I'm not going to require you guys to know, but I just want to introduce to you, there's a formal name based on the length of the carbon chain. So this is dodecanoic acid. Remember, oic is for carboxylic acid, and dodecanoic, dodec, stands for 12. I'm not going to expect you to remember that. But because this systematic naming came up after we discovered these things, there's a common name. People don't use the systematic naming. People always use the common naming. I never really hear of people in journal articles or anything calling the fatty acids by the systematic name. Here we have the trans, and we have the double bond, the linear in quotes, and this is oleic acid, and it has a kink. All right, let's talk about what happens. When you have a saturated fatty acid, can you see as we are increasing the number of carbons, what's happening to the melting point? It's increasing. So remember, melting point, you have to break the intermolecular forces in order to go from solid to liquid. The only intermolecular forces that you're going to see here in a hydrocarbon chain is going to be the dispersive forces. The longer the chain, the more dispersive forces that you get set up. Remember, we talked about this way back in January. Do you guys remember that? The more that you've set up, and it's like Velcro trying to pull them apart, it takes more energy. So lauric acid might be only this long, so you only need this much energy to pull apart. It's a short thing of Velcro that you have to pull apart, not as much energy. But arachidonic is 20 carbons long, so maybe you have this much contact, so you have to pull apart more Velcro that I'm talking about that will require a higher amount of energy, a higher temperature in order to reach the kinetic energy required to break those intermolecular forces. So increasing carbon length, you increase melting point. How about unsaturated fatty acids? 16 carbons, 63 for the melting point, minus 0.5 for the melting point. Holy cow. Look at that. For a 16 carbon chain length, if it's saturated, the melting point is 63. If it's unsaturated, just with one double bond, it's minus 0.5. So one double bond has that much of an effect. So what you're having with the 16 carbon chain is you have this much contact lying flat on. When you have even one double bond, this is what you have. Oh, this is too much stretching for me. Okay, so you only have this point of contact and my elbow point of contact. So that's much easier to break apart. So this kinked structure causes fewer points of contact between the molecules, thus requiring less energy to pull apart and melt. So here with the double bond, we indicate in sort of a numbering system. We say the number of carbons, the number of double bonds, and then this delta with the number on it, that's on the carbon number that it's the double bond is positioned at. So 16 carbons, one double bond. The double bond starts at carbon number 9. Let's count. Here's carbon number 1. The acid is always going to be carbon number 1. Then we have 7 CH2s, right? This is what we mean by the 7 here. So CH2, CH2, all the way 7 of them. So that's 8, and then this is carbon number 9. So that's where you're starting at with your double bond. So here, because we have a longer chain, it's going to increase the melting point, but it's still way lower than that of the saturated. Here, we have still 18 carbons, but instead of just one double bond, we put in 2. And it's then carbon number 9 and carbon number 12. Look what it does to the melting point. It's going to decrease it. It's also omega-6. Omega-3, oh, look at that. Omega-3. I don't know why this is called omega-6. I'm not quite sure. But this is omega-3. It has 3 double bonds. It lowers it even more. Not as strikingly as going from saturated to unsaturated, right? But it does have an effect. The more double bonds you have, the lower the melting point. Arachidonic acid, 4 double bonds. That's just crazy. Minus 50. So that's going to be liquid. Can you tell, excuse me, when you have an unsaturated fatty acid, what is it, the state of the matter going to be at room temperature? Is it going to be liquid or solid? It's going to be liquid, also known as an oil, right? And here, the fatty acids at room temperature are going to be solids. So they're solid fats. Increased number of carbons, you're going to raise the melting point, higher degree of unsaturation. What I mean by that, higher degree of unsaturation meaning more double bonds. It lowers the melting point. All right, now let's put those fatty acids together with glycerol to make our triglycerides. So here's our molecule of glycerol. It has 3 carbons, and every carbon has an alcohol, a hydroxyl group. These are the different names. So poly, many, hydroxy, OH, propane, 3 carbons. So what we're going to do is form 3 ester. Oh, do you guys remember your functional groups? Ester, the old lady name. It's going to be the acid, but not you don't have that hydrogen. You have a carbon on the other side. And then you're going to have 3 fatty acids connected between the acid and the alcohol. So an ester is created, and we'll see this a little bit later, when you react an alcohol, and we have 3 different positions, with an acid, with our fatty acid. And they're going to connect at these points. It's amphipathic because of that ester is going to make it polar, and then you have the nonpolar tails. Of course, triglycerides are found in fat cells, and of course they're stores of energy. We get more energy from the oxidation of fats than we do from carbohydrates. This is backfired on us in the 1980s. We were told to eat more carbohydrates than fats, and everyone got crazy with that and gained about 50 pounds. And now we're told to eat more fats in our diet. So you need it. You definitely need it. All right, so let's take a look at this. Here's our glycerol molecule. And what we're doing is we're condensing it with fatty acids. Remember that these lines here, every point is a CH2 and the end is a CH3. So what we're doing is we're reacting the OH with the acid to get an ester. Remember, an ester is C double bond O, so the carbonyl with the oxygen, so that's just like our acid, but instead of the hydrogen from the acid, we have another carbon. Our ester is particularly stable Are they particularly stable? Or people that have taken organic, are they particularly stable? Do they survive long under not normal conditions? No. They get broken up very easily. So once this is going to hit your stomach, the triglyceride, it's going to get broken up. We have enzymes that will break them up. We'll talk about that later. Now here, we're showing that the fatty acids are all the same. That's not normally what happens. Usually we combine different kinds. So here we have them different lengths, and here we throw in an unsaturated one to show the kink in that. So triglycerides, triglycerides, again, the glycerol and the fatty acid come together. And I really want you to know that what is formed is that ester bond. So what does this double bond do to the packing? What does it do to the packing? It's going to mess it up, right? I mean, I don't like this picture. It looks like these are far apart. Really, they're going to be packed close together. Here, we're showing the kink in this one. Now, as I mentioned in the last slide, you can break these up. You can break this up pretty easily. Enzymes help out with it. So here we have actually different enzymes to break up different ones, but here lipases break them up with water, and you get your fatty acids. Then we're going to look at next chapter how we get the energy out of these fatty acids. Does anybody buy or make homemade soap? No? You go to the farmer's market and buy the little nice soaps. So they might start out with animal fat, and they're going to take some lye or sodium hydroxide and react it with it. And then you're going to get this ionized fatty acid. So saponification, making soap, is going to be the reaction of sodium hydroxide or lye with the triglyceride, with animal fat. And that's how they made it in the olden days. And remember, this makes this part of the molecule, the acid part, particularly hydrophilic. And then you have the long chains. So that's how soap works. You have the long chain that gets dissolved in the oil in your hands or wherever, anything nonpolar. And then what happens is you get this, so here's the surface of my hand. Here's a pile of grease, right? And what happens is the nonpolar tail gets dissolved and the polar head sticks out. So the nonpolar tail dissolves in the grease, and then the polar head gets exposed. So when water comes by, it's going to be soluble in water and carried away. So when my children go to wash their hands and they pump the soap and then just put it underneath the water, I say that is not cleaning your hands. You have to get that soap dissolved in the grease in your hands. So when you're using soap after you use the restroom, are you expecting there to be grease on your hands? I hope not. I don't want to know. But anyway, so really, and this happens a lot on campus, there's no soap. All right, so here's two pictures of a phospholipid. So what we're doing with a phospholipid is we're taking away one of the fatty acids, and we're putting a phosphate group on it. It's called a phospholipic acid, but I'm going to call it a phospholipid. There's too many different phosphoacylglycerols, phospholipids, or phosphatidic acid. Those are three things to say the same thing. So this cartoon and this structure are the same thing. Right here, this cartoon here, the space fiddle, and this are the same thing. So you can see you have your two long tails. They don't have to be identical. And then you have your phosphate head. So this phosphate head makes it very, very polar. And then you have your nonpolar. We can do some crazy stuff. We can put together other groups on top of this phosphate. We can throw stuff on this other end. So here is our just plain phosphatidic acid. All right, you can have two different fatty acids. Remember, R is this restive molecule that we don't really care about. It's just going to be our long hydrocarbon tail chain. And then an ester is when we take away this hydrogen and we put another group. You guys okay? Anything? Did you miss something?
You take the OH to add the phosphate group from 5 to 4. Is that what
So here we have the 3 carbons, right? In the other, here we had the 3 carbons and then we had 3 fatty acids. Now here we're going to take one of the fatty acids away and put a phosphate group. That's a phosphatidic acid. An ester is when we are going to add another group on the other side of it. And I'm showing you that right here. We're going to put an R group here. And so that's where we have the phosphatidic ester. It's still very polar, but there's some crazy stuff we can do with that. And we can do crazy stuff with these fatty acids. It can be 2 different groups. So that's where that ester comes from. Now, let's talk about what we can put there. All right, let me make sure. So when you take that hydrogen off of our phosphatidic acid and make it an ester, if you put this group there, you get cephalin. All right? If you add this group there, you get choline. Okay? Or phosphatidylcholine. So people might be taking that as a supplement. We can get super crazy. Now, one thing I want to mention about this choline, let's take a look at this nitrogen. This nitrogen is what kind of nitrogen? It has 1. How many carbons does it have hanging off of it or attached to it? 4. This carbon and then these 3. So it's a quaternary amine. When you have a quaternary amine, it's permanently positively charged. So by putting this choline over here, you have a negative charge next to a positive charge. So they're amphipathic components, and they are important parts of membranes. And we'll talk about them more when we get to membranes. Here's a couple more. Look at this. Look at this. When we put another a phospholipid that has the ester. So here's sort of like a bridging molecule. This whole group right here is right there. So you have this whole thing, 2 fatty acids, the phosphate, this group, another phosphate, and another glycerol molecule with 2 more lipids going on there. I'm not going to ask you to remember it. I just want you to appreciate how crazy it can get. Yes, Alice?
What's that one do?
Huh?
What does that one do there?
This is in heart tissue.
Oh, really?
So this is cardiolipin in heart tissue. So this is the fat in heart tissue. Any other questions about phospholipids? Waxes. They don't really do a lot biologically. They are when we put together a long chain fatty acid with a long chain alcohol. Look how long these chains are. So that's a definition. You can put together, to make any ester, an alcohol and an acid. But what a wax differs from any ester is that it's 2 long chains. Both the acid and the alcohol are long chain. And they're protective coatings for our plants and animals. Your Flora and Auto Wax, if you buy Carnauba wax and put it on your car, that's going to be this one. And this one, if you get from Wales, this one. Now, how about apples? When you buy an apple, they tend to be like sort of not shiny. You shouldn't buy shiny apples because or if you go apple picking, anybody go apple picking in the fall? Yeah, that's fun. But the apples are not shiny. And the reason why they're not shiny isn't because they've sprayed chemicals on them. It's because they have a natural wax on them to protect them, to keep them fresher. So really what you want to do is when you buy apples, make sure that you don't buy the shiny ones. Those are going to go bad quicker. Buy the ones that are sort of waxy looking, because that has the protective coating on them. My husband likes to joke with me. Last time we went apple picking, he said in a really loud voice, because he could see the owner of the apple orchard, he's like, oh, don't pick the ones that are not shiny because they have the chemicals all over them. And of course the guy's like, wait a second, because he knew that it would just send me into a tizzy. So, I know, you're supposed to have the wax. So, and if you don't bathe your dog on a regular basis, when you pet them, they
Yeah.
kind of,
Oh, I know.
yeah, that's protective coating. They want to be like waterproof, right? You don't want the dog to get like completely wet when you're out in the rain, because they're supposed to be out in the rain. But we gave our dog a bath outside, and all he did was bite the sprayer. Very funny. Anyway. All right, I'm just going to enjoy saying this word, Sphingolipid. It's just fun to say. So, in our fatty acids, our triglycerides, we're putting together glycerol with different fatty acids. In a sphingolipid, instead of putting different things on the glycerol molecule, we're going to put different things on a sphingosine molecule. Does that make sense? So the backbone really to our triglycerides is that 3-carbon, 3-OH glycerol. In sphingolipids, they're the molecule sphingosine, which is in this brown part. This picture's okay. I have one in the better, a better picture in the next slide. So sphingosine is 18 carbons long. It has a long chain tail. Has an alcohol. It has this group here and an amine here. So we see it in the nervous system. And it plays a role in membranes as well. Ceramides are the simplest one. And it's really basically just having a fatty acid attached to the amine of sphingosine. You'll see ceramides in signal transmission in nervous systems. If you put a sugar group on this molecule, which we'll see in a moment, then it's called a cerebroside. See that side ending? That indicates that there's a sugar on there. I just think this from your textbook is a little bit easier to see. Here's our sphingosine. So it's sort of like our glycerol. So you have the OH. Instead of 3 OHs, we have basically 2 OHs and then an amine. Does that make sense? And we're adding onto it a long chain. Here, a ceramide is just where we're going to condense a fatty acid with the amine portion. And here, we're going to add on to this alcohol here, we're going to add on this phosphate group and this quaternary amine. And so sphingomyelin we find in the myelin sheath around nerve cells, and it allows nerve impulses to flow. And if we don't have it, then we're going to have multiple sclerosis. Okay? So let's get crazy. So we understand the basis of it. It's a lot like glycerol, but we have an amine here and then a long chain off the top. So that's the difference between sphingosine and glycerol. An amine and this long chain, and we can do crazy things to it. Look at this. Here, this is our long chain, 1, 2, 3 carbons. the OH, the amine, and instead of the OH, we're going to put it in with a sugar, and this is a glucocerebroside. And we find it in nerve and brain cells. We can have gangliosides, which I'm not even going to show here, that get even crazier. So those are our sphingolipids. What I want you to know is, let's go back. If you're going to remember one thing, I want you to remember the structure of sphingosine, and basically, maybe you can just remember what a ceramide. And actually, I do want you to know when you put a ceramide with another glucose, I might not ask you to draw it, but that you get a cerebroside. And you find it in brain cells. Steroids all have this structure. All of our steroids have these fused rings. And we identify them by letter. So we can, when we're discussing steroids on the street corner, we can say we have this at the 12th carbon, or here in the B ring, we've got this going on. So it's 3 6-membered rings fused, because they share carbons, and then a 5-membered ring. Very, very rigid. Cholesterol, the most important one biologically, is cholesterol. We need it. All right? It's got this floppy tail of hydrocarbon, very rigid. And is it hydrophilic at all? Do we have anything polar there?
One OH group?
You have one OH group. It doesn't really do much. So it's going to, just like our acid part of our fatty acid, when you have 20 carbons in our chain, in our fatty acid, the fatty part, and then one acid group, it's not going to be soluble in water. When you have such a long part, so in fatty acids, they're not soluble in water, even though they have the acid part, because really the fatty part, the nonpolar part, takes over. Same thing with the cholesterol. It's not going to be soluble in water because you only have this measly little OH group. It's not doing anything for you. But I want to point out that this cholesterol has this very rigid group here, and then a floppy tail. So it has both a rigid and a flexible part. And we're going to use it as, what I like to say is like a piece of cardboard in our membranes, sort of to regulate all the floppiness that can happen inside a membrane, sort of like adding some stability to it. Not a lot. That's why I say cardboard, not a wall. It's not a wall. It's just like a little piece of cardboard to keep it from going too far. And that's only one hydrophilic OH group. Rigid, very, very rigid, and that flexible tail. All right, so we need steroids. We need cholesterol to, what we say is, broaden the melting temperature, because the membranes are so floppy inside. They have those fatty acid tails in there just flopping around. What we're doing is we're putting in the piece of cardboard, the cholesterol in there to make it a little bit more solid, to give it a little bit more rigidity, so it doesn't go from being floppy to melting apart. So that's why we say that it increases the temperature range in which the membranes remain flexible. All right, so steroids are also a precursor to sex hormones and vitamin D. So of course you can see this fused ring structure and testosterone, estradiol, progesterone. You can see that there's different things going on, and but you still recognize that fused ring system. If we have extra cholesterol, then you can get atherosclerosis. We'll talk about that in a moment.